This is the homework solutions for chapter 20 in the physics book, the chapter on electric current, resistance, and Ohm's law. The first problem is actually problem number 1. It states, what is the current in milliamperes produced by solar cells of a pocket calculator through which 4 kiloohms of charge passes in 4 hours? So the current is the amount of charge that passes through a circuit over a period of time. So in this case, we have 4 kiloohms of charge passing through. By the way, 1 amp is equal to 1 kulohm per second. That's the unit for current. And in this case, we have 4 hours, and then there are 3,600 seconds per hour. And therefore, these 4's cancel, so it's essentially 1 over 3,600. And if you do the math here, you get 0.273 milliamperes. Now I got that because the answer was 0.000273 amps. And so then I just moved it over 3 spaces, and that's milliamperes. Number 3 states, what is the current when a typical static charge of 0.25 microcoulombs moves from your finger to a doorknob in 0.1 microseconds? Well, again, current is equal to the change in charge over the time it takes for it to move. Current is the movement of charge. So this is 0.25 microcuries, and it all occurs in 1 microsecond. So the micros basically cancel each other out. And so you end up with 0.25 amperes of charge. Number 10. A clock battery wears out after moving 10,000 coulombs of charge through the clock at a rate of 0.5 amperes. So the total charge that's moved is 10,000 coulombs, and this occurs with a current of 0.5 milliamps, 0.5 milliamps, or 0.0005 amps. And the first question here is, how long did the clock run? So A is, how long did the clock run? And if you say that I is equal to delta Q over delta T, then delta T is going to equal, this is I, sorry, is going to equal delta Q over I, which is going to equal 10,000 divided by 0.0005, and that's going to equal 2 times 10 to the 7th seconds, or if you wanted to, it's 5.56 times 10 to the 3 hours. But this answer is good enough. B asks the question, how many electrons per second flowed? Okay, so NC, the number of electrons, is equal to the total change in charge divided by the charge per electron. Okay, and so you have the 5 times 10 to the minus 4 coulombs per second That's what an amp is. And it asks per second how many electrons were moved. And each electron has a charge of 1.6 times 10 to the minus 19 electrons, or charge per electron, I guess is the best way to say it. And you end up with 3.13 times 10 to the 15, and this E comes up and it becomes electrons per second. The Q's cancel, or the C cancels each other out. That's what I wanted to put in there. So that's the answer to that. Number 16. Number 16 states, a 14-gauge copper wire has a diameter of 1.628 millimeters. What is the magnitude of current flowing when the ship drift velocity is 1 millimeter per second? Now you have to look at the example that they give here, because that's where they talk about drift electrons. And I will not give you a question about drift electrons on a quiz. But you have a diameter of 1.628 millimeters, which is a radius of 0.814 millimeters. 0.814 millimeters. And it tells you that the drift velocity is 1 millimeter per second. So first you have to calculate the area, because you're going to need that. And the area is going to be pi r squared. So it's pi times, and the best way to do it is to convert this to meters. So this is 8.14 times 10 to the minus 4 meters squared. So the area equals 2.08 times 10 to the minus 6 meters squared. Now, why did I say that we're going to need this? Well, if you look at the formula in that example problem 23, I is equal to N Q A times the drift velocity, okay? N is the number of electrons. Q is the charge per electron. This is the area, and V over D is this drift velocity, okay? And so this millimeters per second is 1 times 10 to the minus 3 meters per second. So if you put all this in here, you end up, again, looking at that example, it tells you what to put in for N, because that's a standard number. It's 8.34 times 10 to the 28th times 1.6 times 10 to the minus 19, that's Q, times A, which is 2.08 times 10 to the minus 6, times 1 times 10 to the minus 3. That's the drift velocity. And if you multiply that whole thing out, you get 27.7 amps. 17. 17 gives you this sphere, which is a storage ring that is 72 meters in diameter. It's at Stanford, and it has a 20 amp circulating beam of electrons that travel at the speed of light. How many electrons are in the beam? Okay, so you have the current is 20 amps, which remember is 20 coulombs of charge per second. The diameter of the ring is 72 meters. Now, why is that important? Well, you want to know the entire path that this stream of electrons has to take. So you need the circumference, and the circumference is pi d. And if you do the pi d, you get 226 meters for the total path that these electrons have to cover. The velocity of electrons is equal to the distance that it covers over the time it takes to cover it. And so the time it takes to cover it is equal to the distance divided by the velocity. It tells you that the velocity of light, they travel at the velocity of light. So that's 3 times 10 to the 8th meters per second. So the amount of time, and you're going to need that for this part, per second. So the amount of time here is 7.53 times 10 to the minus 7th seconds. And so it can make one full circuit in that period of time. So now you know that I is equal to the change in charge divided by the change in time. So that tells you, so in order to find the change in charge, which is how we're going to figure out how many electrons are in here, you take I, which is 20, times the time, which is 7.53 times 10 to the minus 7. And that tells you that the total charge is 1.51 times 10 to the minus 15, or 5, excuse me, coulombs. And then Q, or the total number of electrons, is going to equal that number of coulombs, times the number of electrons per coulomb, which is 6.234, excuse me, times 10 to the 18th electrons per coulomb. That number there is just the inverse of 1.6 times 10 to the minus 19. And so if you do that, that equals 9.4 times 10 to the 13 electrons in this beam. Now, number 18, we're shifting over to Ohm's law, and Ohm's law is V is equal to IR, okay, just so you get the basis for that. And the first question is, what current flows through the bulb of a 3-volt flashlight when its hot resistance is 3.6 ohms, okay? So if V equals IR, then I is equal to V over R. So that's a 3-volt flashlight divided by a 3.6 ohm resistor. And so that'll tell you that it's 0.833 amps that flow through that bulb. Number 22. Find the voltage drop in an extension cord having a 0.06 ohm resistance and through which 5 amps is flowing. Okay, so V is equal to IR. So that's equal to 5 times 0.06. So the voltage is 0.3 volts. The second part of this problem says that if you change or use a cheaper cord, and now the resistance 0.3, what's now the voltage drop? So it's the same calculation. Now it's 5 times 0.3, or 1.5 volts. So if you look at this, this represents the energy needed to pass these electrons through this cord, and you see that there's an increase in the number of electrons that pass through the cord. C says, why is the voltage to whatever appliance is being used reduced by this amount? Okay, the voltage is reduced because the resistance is reduced. It takes less energy to pass an electron through a cord if there's less resistance. Think of it like a garden hose. If you have a thinner garden hose, it takes more pressure to push the same amount of water through that garden hose than it does if the garden hose is bigger. So if a big garden hose represents this amount of resistance, so it only takes this much pressure, whereas a smaller diameter garden hose pushing the same amount of water requires greater pressure. Okay, we're going to stop at this point and move on to the next part with the rest of the problems.